Welcome to Lesson 4C, Hearing and Noise, Part 1.
This is section 3.4 in the textbook, and we're going to discuss how hearing works quickly, and then we'll look at the equations. So how does the ear work? The outer ear amplifies and directs the sound into your ear canal, and then you get to the eardrum, which is technically called the tympanic membrane. That is connected to this malleus, which is a little bone, which we often call the hammer. And then we have the incus next, and that's often called the anvil. It looks sort of like an anvil. And then this one really looks like a stirrup. We call that the stapes or stirrup. And then those little bones are designed so that they amplify the sound and send it into this snail-like organ here called the cochlea. And that's where the hearing actually takes place. How does it work? As the vibrations and the pressure changes go through this kind of snail spiral, if we magnify a portion of that, you have your skin, your tissue, and then on this tissue along this wall are little hairs. They're called cilia, just like in the bronchial tubes. We talked about cilia, just little hairs. They vibrate as sound waves hit them, and there's little nerves attached to them that all collect together. These are different lengths as you go around this spiral. Some of the big ones hear low frequency sounds, the real tiny ones hear high frequency sounds, and these all go to the cochlear nerve, which is here. So this goes to the brain where it has to process all that information. Each one of these little hairs sends a signal, and we can hear different frequencies, and how much they vibrate back and forth gives us the sound level or the amplitude. So it's actually a pretty cool design. Eustachian tube goes to the throat. When you get a bad cold, this is blocked with mucus, and then your ear feels like it's muffled. It's designed to equalize the pressure between your inner ear and your throat. That's how the ear works. I want to talk about some equations and sound levels. I just wanted to point out, if you want to read the book, I'm not going to go over this, but the first couple sections talk about the physiology and some hearing diseases. So things can go wrong with your hearing. You can read that on your own. From engineering point of view, let's look at the equations. And first of all, why is noise important? In terms of indoor air quality, even a well-designed air pollution control system, abbreviate that APCS, won't work if it is off. And why would it be off? If it's too noisy, people will tend to turn things off. There's also OSHA standards for noise levels, what's acceptable. A high noise level can lead to hearing loss. If you go back to these cilia, if you hear loud noises for a long period of time, some of these cilia start to break. You'll lose your hearing in that frequency range. And so as you get old, everything in your body gets sort of stiffer, and so old people lose these naturally. They start breaking and falling off, and they don't get rejuvenated, so you lose your hearing.
Oh, what did you say, Sonny?
I said you could lose your hearing when you get old.
Oh, I hope that doesn't happen to me.
Loud noises make that happen much more quickly.
Is that why my mom always tells me not to listen to loud music? Yes, BJ, your mom is right.
We have some noise source. It could be a piece of equipment, it could be music, it could just be like loud noise, like a jackhammer. Let's look at the sound waves that come off of that. So of course they spread out. I'm drawing it on a page, but these would spread out spherically. And then we have from that noise source radius r. And then let's suppose we have an ear or a microphone that's hearing the sound. So what are the equations that are important? First of all, the parameters that are important. There's the sound pressure. We'll call this P. So that's a force per area. We have a sound intensity, capital I. This is a power per area. And then we have the sound power, capital W, and that just has dimensions of power itself. With these, we'll define some non-dimensional parameters, and these are what we're going to actually use for our equations. L sub P is the sound pressure level in units of dB, a sound intensity level also in dB, and then we'll have LW, the sound power level, also in dB. All of these are non-dimensional. dB is one of these non-dimensional units, and here's how we define these guys. LP is equal to 20 log. These are log base 10s, not natural logs. 20 log base 10 of P over P naught in decibels, and P naught is the approximate threshold of human hearing. You get healthy people, not old people, and this is typically done at the middle range of your hearing, 1,000 hertz. If you hear this tone, you've done this in the doctor's office if you've had a physical, and they keep going lower and lower until you can't hear it anymore. P naught turns out to be 2 × 10 to the -5th Newton per meter squared. And similarly, LW, sound power level, is 10 log 10 of W over W naught, again in decibels. This W naught is also the threshold of hearing, and that's typically around 10 to the -12th watts, which is extremely small power. Even this pressure is extremely small, 2 × 10 to the -5th Newton per meter squared. An atmosphere is 100,000 Newton per meter squared. This is the sound power level, or also called the acoustic power level. The big difference here is that LW is independent of distance, this radius R, distance from the source. LW is independent of R, but LP depends on R. LW is caused by the noise, and it doesn't matter who's listening or how far you're standing away from it and hearing it, it makes some sound. It's just the power of the sound. So this sound source is where we talk about our LW, and then at the hearing location, that's where we talk about LP. I have a summary of equations and tables from our textbook. This is the most important equation. We'll always be using sound pressure level in dB. This is what most people talk about when they say, how loud is the sound that you're hearing? And the answer is this value in dBs or decibels. This is the reference value. I'm going to skip sound intensity levels. Those are defined the same way. Li and LP are the same. So we're only going to use LP as our primary indicator of sound level. The sound power level, or the acoustic power level, I defined here. And again, LW is due to the source, and it does not depend on R. By the way, this is also in dB. Anything with a logarithm is non-dimensional. This has to be non-dimensional, and so this is just a non-dimensional number, but we call it a decibel. Those are both in decibels, so we can add them up in our equations as we need to, as you'll see. This does depend on distance, so this is associated with what you hear, whereas this LW is associated with the source, what is produced, independent of who hears it. We're also going to define a reference distance. When we talk about distance R, some textbooks get a little lazy when they have a logarithm of radius, so they'll just do log of R. But that is meaningless because it depends on units, and this is mathematically incorrect. When you have a log base 10 or a natural log, whatever's in the log should be non-dimensional. So what we do in our textbook is define an R over R naught, where R naught is just 1 meter. So as long as you convert R to meters, this will be non-dimensional. So that's why you see these R naughts appearing in these equations. I'll call this our workhorse equation. That's the one that we use for all our calculations. We've already defined the radius, and R naught is 1 meter just to make it non-dimensional. This is a relationship between the sound power level and the sound pressure level. We also have this Q. It's called the directivity factor. It depends on how many walls are nearby. It also depends on the hardness of those walls. Q is equal to 1 in what we call free space, and that means there's no reflections, no walls. So you're out in free space. Now, if you were in space, you wouldn't hear anything because it's a vacuum, but we mean in air. So you just have your source, and it's making sound waves that are spreading out radius R in 3D, of course. And there's no walls around to hinder that. I'm in my office right now recording this, and there's walls all around and a ceiling and a floor, so I am not in free space. So how do you measure something like this? You typically use what is called an anechoic chamber, which means exactly what it sounds like. There's no echoes. They're kind of cool to go in. It's a room, and on all the walls and the floors are foam rubber, very absorbing material in this kind of corrugated pattern. So any sound waves that hit those get absorbed and reflected around a little bit and absorbed into the walls. So it simulates a free space where if you have a source and it's radiating sound, that's just like a free space. Q equal 2 means that you have one reflective wall. That means it's hard, like solid concrete or solid hardwood or metal that's reflecting, not carpet or something mushy. Let's just use a floor, for example. And you have your source right there, and it's starting to reflect sound. Well, what happens is you're going to get both the sound itself and the reflection from the wall. Mathematicians like to put an image source underneath, and then you can draw these waves also. So effectively, you're doubling the waves. What happens is, as you go out, you're going to hear twice the waves. And so when you plug in a Q equal 2, this is for a perfectly hard reflective wall. Notice that you have 10 log 10 Q. And so if I plug in 10 log 10 Q and let Q equal 2, you get very close to 3 dB. The sound pressure level is up by 3 dB. It amplifies the sound because of the reflections. Now, similarly, Q equal 4, that's if you have 2 walls. So this would be like at a vertical wall and a floor. If you put some kind of machinery in a plant and it's right there producing sound, and you start analyzing this, you would have to put an image there and there. Sound is reflecting, and this gets complicated, but you're getting the sound from the source, you're getting the sound from that reflection, you're getting the sound from this reflection. So you're getting all these extra reflections. When you do your 10 log 10 of 4, this gives you approximately 6 dB, and so LP is up by 6 dB. And by extension, if you go to 3 walls, if we have a corner, again, these all have to be hard walls. So you have a floor, you have a side wall and another side wall in a corner. Put your source real close to this corner. You get a Q of 8. 10 log 10 of a Q of 8 turns out to be 9 dB. So each of these is going up by about 3 dB compared to the free space value. And you see in the equation for LP, LW is fixed. That's a function of the source. And then you have this term, which deals with the reflectivity, and then the rest of it will be the same for these cases. So you're just increasing sound level. At this point, I'm going to share a little video that I created about sound reflection, how to amplify your music. I'm going to show you how sounds can be amplified by reflection from walls. So I have this little website called noises.online on my iPod, and I will play Bubbling Creek. When it's in the air, that's a directivity factor of 1, which means there's no reflections whatsoever. Here's a directivity factor of 1. As I get close to a wall, a hard wall, you can hear that that gets louder because it's reflecting, the sound's reflecting and basically doubling the amount of sound emanating. So if you do the math, the decibel level goes up by 3. If you go close to 2 walls, you can hear it get even louder. 1 wall, 2 walls. That's a directivity factor of 4, which is a dB level increased by 6. If you go into a corner, you can make it even louder. From a directivity factor of 4 there to a directivity factor of 8. And that's a dB level increase of 9 extra dB. Again, the directivity factor is about 1 here out in the open. When it's free sounding. If you go close to a soft wall like a carpet, it doesn't change a whole lot. If anything, it dulls it because it's muffling the sound. You have to have reflection from a hard surface in order to amplify the sound. Here's a practical example. I'm listening to a podcast while I work out, and you can hear how loud it is. If I put it on the floor, it's louder. If I put it next to 2 floors, 2 walls, it's louder yet. I put it in a corner, it's even louder. Remember, this LW is independent of where you're at. So LW is due to the noise source. You've heard the old question, if a tree falls in the forest, nobody hears it, does it still make a noise? The answer is obviously yes, it still makes a noise, and that's because LW could care less who hears it. It's just making a noise. That's the source. And then if you talk about LP, that depends on who hears it and how close that person is or that microphone is to the source and how many walls are nearby. Now let's look at soft surfaces. Suppose you don't have a concrete or a tile floor or something like that, but you have carpet, or you're putting this on a chair where you have cloth. You're outside and there's grass. So we can look at a case like, suppose this wall is hard, but this floor is some kind of carpet or some soft material. It's not a hard reflection, and you put your source in the corner like this. Now normally we'd say for that case you'd have a Q equal 4, but instead of 4 it would be at least 2 because of this wall, but less than 2 from this wall. The combination would be somewhere between 2 and 4. Some examples of sound levels in dB. 160 dB is really dangerous. If you were standing right next to a turbojet engine, that's dangerous. You can blow out your ears. Air compressors can be very noisy, 120 dB. Rock and roll band, not so good for your ears. Vacuum cleaner can be 70 dB or so. Normal conversation, if we're in a room talking with people, it's around 60 dB. Quiet room, like my office right now, except for my speaking, is typically around 40 dB. I just bought a Bosch dishwasher and it says 44 dB. They claim is the quietest in the business, and it is indeed quiet. You can hardly hear it. dB, decibels, as measured by a microphone. It's measuring all the frequencies equally, whereas there's something you'll see as dBA, and that's the same thing, except it's measured by a microphone but mimic human hearing. So when we talk about dB, we won't put the A typically, but that's what we're talking about, dBA. Typical range of human hearing is approximately 20 to 20,000 hertz. This is for young people. Old people like me start to lose, especially these high frequencies, because those cilia start breaking off. And so older people can't hear high frequency noises. Quick example, noise level of a factory machine is 85 dB at 10 meters in free space. So that indicates Q equal 1. And this was probably measured in an anechoic chamber. You stick this machine in an anechoic chamber, and 10 meters away, it had to be a pretty big anechoic chamber. You measure the 85 dB. That's not LW, that's LP, but it's at 10 meters in free space. Estimate the sound pressure level, LP, at a distance 4 feet away, so watch your units, when the machine sits in the corner of a building and all walls are concrete. Let's first calculate LP of the calibrated case, and we'll use a subscript C for calibrated. At RC equal 10 meters, we know that LPC is equal to 85 dB, and QC, since it's free space, QC is equal to 1. So using our workhorse equation, LW is LPC plus 20 log 10, the R, which is RC over R naught, minus 10 log 10 QC plus 11.0. And let's call that equation 1. Now, why didn't I put a subscript C here? And that's because, remember, LW is independent of who hears it. So that is a constant for this particular machine. LW is not a function of R or Q. It's only a function of the sound itself. This is all at the calibrated level. At the given distance that we're interested in and the conditions, we know that R is 4.0 feet and Q, since it's in a corner, Q equal 8. So we can write our workhorse equation again. This time I'm solving for LP equal LW minus 20 log 10 R over R naught plus 10 log 10 QC minus 11.0. That's our workhorse equation again, and we'll call this 2. And now we plug 1 into 2 and do some algebra. Anytime you see this wavy arrow going down, that means algebra that I'm not showing. You can do this on your own. I just wanted to show you the result, but I wanted to first identify some identities that are critical here. These are math identities that you should know, but you may not remember them. These work for ln too, a natural log, but we're doing all this in log 10. Log base 10 AB product is equal to the sum log 10A plus log 10B. Log 10A over B kind of follows from that. That's equal to log 10A minus log 10B. C log 10A equal log 10 of the quantity A to the C. Again, I like to keep everything in variables until the very end. And so after all this algebra, we end up with LP equal LPC plus 20 log 10 RC over R plus 10 log 10 Q over QC. That's our final answer in variable form. When we plug in the numbers, we get LP equal, remember the given value of the machine was 85 dB at 10 meters in free space. So 20 log 10 RC was 10 meters and R was 4 feet. So we convert that to meters. We add the 10, these are all log 10s of Q. The actual Q is 8 where we're hearing this, and QC for free space was 1. And this turns out to be 112.3 dB. Generally, we round to the nearest dB. My answer would be 112 dB. The most important thing to remember is that LP is a function of R and Q, and LW is a constant for a given source.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's what